Used into this sort of three additional components. One is aging chains and higher order delays. And I want to use that topic as an opportunity to emphasize why we call these things delays in the first place. Second thing is the issue of competing risks. And we actually saw a glimpse of that last time when we had a stock which was drained by two flows, which were in some sense competing with each other. The occurrence of one precluded the occurrence of the other. And finally, there's issues of delays and oscillations that I'm going to not talk about this lecture, but the fact is oscillations arise from situations where we have delays associated with things. And so the most easy way to represent that is with two stocks, and that's where we start getting oscillations coming in. Physicists know it from harmonic oscillators and trying to represent those, where you have velocity as well as position, for example. So we saw first order delays last time. First order delays are kind of the simplest feedback mechanism. Certainly one of the simplest. So we have some stock, it's let's say drained, and we have some time constant associated with it, or we have some rate constant. So if this is a time constant, it's some mean delay, some mean amount of time you spend in this stock. What's the formula for here, for this? Divided by. And we know that because it's dimensionally correct. The flow has what dimension? If the stock is dimension d, what's the dimension associated with the flow? D over t. It's the amount of d's going per t, right? Per unit time. And so if we have a formula here that's the stock divided by a delay, and the delay is measured in units of time, then it dimensionally makes sense. By contrast, if we have a rate constant, we have a chance per unit time of going down this connection, 1% chance per unit time of losing your immunity state. What is the formula here? Times this rate constant. What's the unit of the rate constant? Per time. What's the relationship of that rate constant, say 0.01, this chance per unit time of going down this? What's its relationship to the delay? It's 1 over it. It's just the reciprocal of it. So if you have an immunity loss delay of 50 months, you have a rate constant, chance per unit time of 0.02 going down, and vice versa. And it makes sense. At a mathematical level, if you have a stock X, and you have a time constant, call it tau associated with it, so this is some delay associated with it. We can either write the flow out as x over tau, or we can write it as x times 1 over tau, right? Just the same thing mathematically. It just, we call this the time constant, tau. We call this 1 over tau, the rate constant. Mm-hmm. Okay, this is the rate constant. So it's just 6 of one, half dozen of the other. It's just there are different ways of naming things. So it's a labeling. So that was a little bit on sort of mathematics associated with first order delays. And that is